Hello class, we're about to start lesson 1.8, portion control. Our learning objectives are to describe what apportionment is and why it's used, and to compute standard divisors and quotas, and also to apportion items using a variety of methods. Now, according to our syllabus for section 1A, we are supposed to cover pages 96, 1 through 8, and page 100, 1 through 11. But we're started on page 95, which is the actual start of section 1.8. Okay, now we're going to go down here to the bottom. It says here, the most common example of apportionment, and as we'll see where the study came from in the first place, is the United States Congress. There are 100 senators in 50 states, 2 senators per state, easy. But in the House of Representatives, the number of representatives is based on the population of the state. There are 435 seats in the House, and they're divided according to population. For example, Florida has 25 seats, Pennsylvania has 19, and Rhode Island has just 2. So why can't we just divide 435 by the population to find out how many representatives per person? Then multiply by the state's population, because it's against the law to divide politicians into pieces. Also, almost every state will be entitled to a non-integer number of seats, which won't work. That's where apportionment comes in. Apportionment is the process of fairly assigning identical indivisible objects among individuals entitled to shares that may be unequal. We just pointed out that the most logical way to attack dividing up the seats in Congress would be to divide the entire population by the number of seats. This would tell us how many people on average would be represented by one congressperson. This number is known as the standard divisor, and it plays a really important role in apportionment. So we'll highlight the formula next. But don't think about memorizing it. Think about what it means, and you'll have a much better chance of understanding this lesson. Throughout this lesson, we'll refer to the objects being assigned as seats, like seats in Congress. The individuals they're allocated to will be called districts. Now, on page 96, we have the standard divisor formula. The standard divisor for an apportionment process is the average number of people per seat. Standard divisor is equal to the total population divided by the number of seats. Here's the apportionment problem we'll be working on in this lesson. A large city has 20 seats to be allocated proportionally among 5 districts according to the population of each district. The populations of the districts in thousands are shown in the table. So we have districts 1 through 5, and we have the population here. Even though we see 32, 80, 41, 67, and 20, remember this is in thousands, so it's really 32,000, 80,000, and so on, to the total population of 240, which is actually 240,000. Now, number 1, it says explain why it wouldn't be fair to just assign 4 representatives to each district. If you notice here, all of their populations are different. So I'm pretty sure a person with population 80 would not feel right having the same representation as someone with as a district that only has a population of 20,000. So we could put the population are very different. So the representatives should be also. Now we go here to number 2. It says, find the standard divisor for the apportionment. Now, going back here to the top with our standard divisor formula, We're going to abbreviate it with S period D for standard divisor, and that equals to the total population divided by the number of seats. Now, if we look here, the total population is given to us. We can use this as 240,000, and then we would divide that by 20, because we're told early in the problem that there are 20 seats to divide by. And remember, this 240 is in thousands, so that's how we get the 240,000. When you divide this out, you'll get 12,000. So 12,000 is your standard divisor, and that means, on average, there should be 12,000 people per one seat of representation. Now, number 3, it says, notice that District 2 has exactly 1/3 of the population. So if we go back up here, it's 80. 80 is 1/3 of 240. It would seem perfectly reasonable then for that district to get 1/3 of the seats. Why won't District 2 get exactly 1/3 of the seats? Now, watch this. There are 20 seats, and we say that District 2 is 1/3. So we could divide 20 by 3. When we divide 20 by 3, that would give us 6 2/3. We know we cannot have 2/3 of a seat, so 6 2/3, it does not divide out evenly. That's why we cannot give District 2 exactly 1/3 of the seats. Now we move on to page 97. It says, first of all, did you get this? This may be a classroom activity, but we're going to start back here picking up with the lesson. It says, while we've seen that you can assign seats simply based on what percentage of the total population a given district has, that percentage still plays an important role in apportionment. If we divide the population of a given district by the standard divisor, something interesting happens. Now, what happens is we end up with a value over a fraction. Now, in problem number 4, it says, given the fact that dividing by a fraction is the same as multiplying by its reciprocal, fill in a blank to rewrite the division above as multiplication. So we will have the population of the district times the reciprocal. So that means number of seats will go in your numerator, and in your denominator, it'll be total population. So now, it says now we can rearrange the multiplication a bit using properties of multiplying fractions. So, just to show an illustration, if you had 6 times, let's see, 5/10. Okay, we know this will end up being 30 over 10, which is 3. All right, now, what we're about to do is switch this, since this is multiplication. We can make this 6 over 10 times 5, and that would still give us 30 over 10, which is 3. So, shifting the denominator does not change the value of the problem, which is what they did here. They took the population of the district and put total population below it and times number of seats. So the problem has not changed. So now, we come here to number 5. It says, compare this to the line of reasoning in question 3. The fraction part of the above formula is exactly the percentage of the total population that lives in a given district in decimal form. With that in mind, perform the calculation in the formula above for District 3 in our example problem. Then write a description of what the result of the calculation tells you. Okay, now, if we go back to the previous page, District 3 has a population of 41 or 41,000. So, what we would need to do is take the population of the district divided by the total population multiplied by the number of seats. Okay, now the population of the district, we said it was 41 or 41,000, so we'll just do 41. And then the total population, which would be 240. As you all see, the total population is 240. And we multiply by the number of seats. We have been told through this problem the number of seats is 20. So now, when we take 41 over 240 times 20, that would give us 3.42. So, what this is saying is they should get 3.42 seats if this was possible. Okay, now we move on to the next page. The formula we built, which is the percentage of the total population that lives in a given district multiplied by the total number of seats, is the theoretical number of seats that each district should get if it were possible to hand out fractional portions of seats. We call this number the standard quota. The standard quota for a district is the population of that district divided by the standard divisor. So standard quota, population of district divided by the standard divisor. It describes the number of seats that each district would be assigned if it made sense to assign fractional portions of seats. Find the standard quota for each district in the city described on page 96. Now, we could take a quick look here. This is what's described on page 96. This has all of the districts and all of their population. So, what they want us to do here, they want us to take each district. I'm just going to do, my numbers will relate to districts. So this would be District 1, District 2, District 3, District 4, and then District 5. So for District 1, it is 32,000 divided by 12,000, which would give us 2.67. District 2, it would be 80,000 divided by 12,000, which would be approximately 6.67. District 3, we actually already solved that, but we did 41 over 12, but we know that 41 is really 41,000, and it's over 12,000, which gave us 3.42. District 4, it would be 67,000 divided by 12,000, which is equal to 5.58. And then District 5, we will add 20,000 divided by 12,000, which is equal to 1.67. Now, these are all the standard quotas for districts 1 through 5. Now that we know how to almost find the number of seats that should go to each district, aside from the pesky issue of fractional parts, the rest of the study of apportionment is about deciding if each district's number of seats should come from rounding its standard quota up to the next bigger whole number or down to the next smaller number. Seriously, that's pretty much it. A logical place to start is by simply using familiar rounding rules. So let's give that a try. So we'll move on to page 99. It says round each of the standard quotas you calculated in question 6 to the nearest whole number. Then add the results and explain why that won't work as the number of seats assigned to each district. So on page 98, you had that on the previous page, we'll deal with the answers for each district. District 1 was 2.67. District 2 was 6.67. District 3 was 3.42. District 4 was 5.58. And District 5 was 1.67. So now they ask us to round to the nearest whole number. We look at that first digit behind the decimal. All the ones that have 5 or more behind it, we go up to the next highest number. So this would be 3, this would be 7, this would be 6, this would be 2. Now this has 4 or less, so then this would go down to 3. And those are the rounded values. Now, we're supposed to add all of these. So we would take 3 plus 7 plus 3 plus 6 plus 2. And when we add all these together, it would give us 21 seats. We only have 20 seats. This is why this does not work. It adds up to 21, but we only have 20 seats. Now we come down here to problem number 8. Now there's a bit of description here as to what we're supposed to do with number 8. It said question 7 shows that simply rounding each standard quotient to the nearest whole number isn't a reliable method of apportionment. The realization dates back to at least 1790, when both Alexander Hamilton, the first Secretary of the Treasury, and Thomas Jefferson suggested methods for apportioning congressional seats after our nation's first official census. The methods of apportionment that we'll study are all based on first calculating the standard quota, then deciding whether to round up or down. For any district, the lower quota is the result of rounding the standard quota down to the next lower whole number. The upper quota is the result of rounding up to the next larger whole number. Use your results from question 6 to fill in the table below for each district. Now, from question 6, first of all, we had our standard quota, which was basically, I have them listed up here. It's the values before we rounded. So for District 1, it was 2.67. District 2, it was 6.67. District 3, 3.42. District 4, 5.58. And finally, District 5, 1.67. Now, the lower quota, we're told to round down. Now, I would tell you, a more practical way of doing this is this here. With your lower quota, it's just the number in front of the decimal. So it'll be 2, 6, 3, 5, and 1. Your lower quota is just the number in front of the decimal. Your upper quota, you could look at this as one or two ways. Whatever that digit is in front of the decimal, you just add 1 to it. And that will give you your upper quota. Or, since you have to do a lower quota anyway, you could just add 1 to the lower quota. So this would be 3, 7, 4, 6, and 2. So this is your lower quota and your upper quota.